Okay, so in this video, we want to cover the last possible complication which can arise in the eigenvalue method for solving systems of differential equations. And this is when you get your characteristic polynomial, it happens that an eigenvalue is a quote unquote repeated eigenvalue. What that means is that a certain factor might appear more than once in the factorization of the characteristic polynomial. Let me give you an example of what I mean. So we want to talk about repeated eigenvalues here. So a very concrete example of this phenomenon would be something like the following. Consider the matrix P equals 2, 2, 0, 0. This is sometimes called the diagonal matrix, are often called a diagonal matrix because the only non-zero entries live on the diagonal. The off-diagonal entries in particular are 0. It's also sometimes called a scalar matrix because notice that the diagonal entries are identical. They're both 2. All right, and this is going to be important. The reason why it's sometimes called a scalar matrix is because if you take any other matrix, if you multiply P times this particular P times A, well, this is just the same thing as, because this is like 2 times the identity, right? You can think of this as being a 2 times I times A, which is just 2A, which is, in other words, just doubling all of the entries of A. So we sometimes call this a scalar matrix. Anyway, none of this is terribly important. Let's think about the eigenvalues of this guy. So the characteristic polynomial is going to be the determinant of 2 minus lambda 0, 0, 2 minus lambda, which you will not be surprised is 2 minus lambda squared. And crucially, this factor of 2 minus lambda, which gives rise to the eigenvalue 2, appears twice in the factorization of the characteristic polynomial. Why does it appear twice? Because of that 2 that's sitting right there. So this is what we want to say about it. 2 minus lambda appears twice in the factorization. So sometimes what people will say, another way of saying this that sometimes people say, is that lambda equal to 2 is an eigenvalue. And this is true. It is definitely an eigenvalue because it's a root of the characteristic polynomial. But we say with algebraic multiplicity 2. This algebraic multiplicity 2 is because 2 minus lambda appears twice in the factorization. Okay? All right. Now, what can we say about the eigenvectors? Well, note that because this matrix P, because the effect of multiplying any vector by P, the effect of multiplying any vector by P is to multiply the vector by 2. Vector by 2. An implication of this is that every non-zero vector is an eigenvector of P. In other words, the eigenvectors, in other words, how can I say it? Well, so what that means is that we can find 2 linearly independent eigenvectors really, really easily. Here's 2 linearly independent eigenvectors, 1, 0, and 0, 1. They're obviously linearly independent because they're not scalar multiples of one another. And these are linearly independent eigenvectors. And this makes writing down a solution to so if we want to write down this general solution to the system x prime equals p times x, this is very easy now. This is going to be given by x is equal to c1 times 1, 0 times e to the 2t plus c2 times 0, 1 times e to the 2t. Okay? We have a pair of linearly independent eigenvectors. Okay? All right. So that's the kind of easy situation. And because we have these two linearly independent eigenvectors, sometimes, and I'm just going to give you the jargon, and you might not feel comfortable with what I'm about to say, but we say that lambda equal to 2 has geometric multiplicity. Two. All right. Now let me contrast that. So I don't stress out too much, because I want to show you another example of a situation which can arise. Let's think about a different system, very similar. It looks very similar anyway. 2, 1, 0, 2. Now you can see this p is very similar to the p that we had in the previous problem, except that that 1, 2 entry is different. This entry right here is non-zero. And that's going to make all the difference in the world, it turns out. Okay, let's study. So first of all, what's its characteristic polynomial? Well, it's 2 minus lambda squared again. Check it if you don't believe me, it's true. Okay, meaning that lambda equal to 2 is an eigenvalue with algebraic multiplicity 2, just like above. Is an e-value with algebraic multiplicity 2. Okay, exactly the same as in the previous example. Why? Because 2 minus lambda appears twice in the factorization of the characteristic polynomial. That's why. Okay? But now it is no longer the case that the effect of multiplying by this p is as simple as just multiplying the vector by p. So in particular, this statement is no longer true about this matrix. We have to actually do some work in order to find the eigenvectors. Okay, so what we're going to do is to find eigenvectors is solve the system. To find eigenvectors, we solve, of course. Well, p minus 2 lambda, 2 times the identity rather, times v equals 0. We want to solve for non-zero v as usual. None of this should feel weird. So if I look at the system, what I get is 0, 1, 0, 0, and then augment 0, 0. Okay? What this is telling me, the 0 row tells me nothing. That second row tells me nothing. That's not unusual. We're used to that. But the first row is telling me that the condition to be an eigenvector now, is that v2 be equal to 0. Not the 0 vector, but rather 0. Meaning that if I take v1, let v1 be anything, then I get a solution to this, this equation right here. This equation. As long as v2 is 0. And if I want something non-zero to give me an eigenvector, then I can choose literally any non-zero number. So I'm going to choose v to be equal to 1, 0. This is an eigenvector with eigenvalue 0. Oh, sorry, eigenvalue 2. My bad. Eigenvalue 2. Okay? So that gives me one solution. But you can see, like, I can't get another solution. I can't get another eigenvector out of this eigenvalue. I have an eigenvalue of 2, which is kind of repeated twice, but I only can extract one eigenvector out of it. What do I mean by one eigenvector? what I mean is I can't find another eigenvector which is linearly independent from this one. Every eigenvector with eigenvalue 2 for this matrix right here is going to be a scalar multiple of 1, 0. So in particular, not linearly independent. Maybe I'll write that. I cannot find a second eigenvector with eigenvalue 2 which is linearly independent. Or, well, can I write it instead? Which is not a scalar multiple of 1, 0. Right? So how that translates into the statement, we can say the statement in another way, that lambda equal to 2, the eigenvalue, has geometric multiplicity 1. Now contrast that with the previous case. Previous case, same characteristic polynomial, identical. Same what we call algebraic multiplicity. Algebraic multiplicity is 2 in each case. However, crucially, in this case, lambda equal to 2 had geometric multiplicity of 2, whereas in this case, lambda equal to 2 has a geometric multiplicity of 1. Okay? So the question is, what do we do in this case? Because we know from general theories that I've shoved down your throat in the past that the dimension of the solution space to x prime equals px, if we think about this system, but now for this matrix, P, we know that the solution space is two-dimensional. Okay? But this only gives us one solution because we can only find one linearly independent eigenvector with eigenvalue 2. There's only one. Another way of saying it, by the way, is that the eigenspace, it's a little complicated. I don't want to define this too carefully, but the space of all eigenvectors is in some sense one-dimensional in this case, whereas in this case, it was two-dimensional. I could find two linearly independent eigenvectors in this case. But here I can only find one. Okay? Question is, how do we find a second solution to x prime equals px? Second solution to x prime equals px, which is linearly independent. From the solution that we know. The solution that we know is 1, 0 times e to the 2t. We know that's a solution because of the whole ansatz, right? V e to the lambda t. V is an eigenvector. It is with eigenvalue 2. So this is a solution right here. But we need a second solution in order to be able to write down the general solution to this system here. So how do we do that? We'll talk about that in the next video.